Hey, welcome to Concept Based. I'm John Hepworth. This is the Year 11 Advanced Trigonomic Identities and Equations part of your syllabus. And we're specifically in these trig identities and equations that we're trying to solve. This is an area that when I was at high school, I sort of found a little bit confusing because I felt like it was more of a memory retention thing rather than a conceptual understanding thing. So this being the channel concept based, I want to try and make sure that you are bringing into these solves as many concepts as you possibly can. Also, when we look at this today, I also want to look at the reference sheet that you have and what sort of guidance can be given to you, what it is that you do actually need to remember and don't, because the less that we have to remember is great, but the more we understand, then we don't really have to remember anything because we understand it. So let's look at this question. Solve root 3 cos x equals sine x, and then it has a domain for negative pi is less than x is less than pi. So we were introduced to radians previously, so we're just working in that radians area. It's pretty much just like a trig equation. So why is it in this sort of trig identity area? Well, let's have a little look at what we're given as trig identity. And that is we're given these. So there are these essentially reciprocal trig functions, sec, cosec, and cot, that can be things that we substitute in to solve equations. And then there's actually one down the bottom there, which I look forward to doing a video on next. I'll do that one tomorrow. Cos squared x plus sine squared x equals 1, showing a proof for that and so forth, and solving a question in it that's a little bit challenging. But yeah, so the one that we're going to be looking at today is we've got this here, cot A equals cos A over sine A. So that's a reminder to you that there is a tan function, and the tan function is the reciprocal of that, so it's sine A over cos A. So in advanced, the only trig identities you're really substituting is a reciprocal function, tan equals sine over cos, or cos squared plus sine squared equals 1. That's it. That's the depth that you have to go in advanced mathematics. Extension 1 significantly further. So hopefully we're able to substitute into identify parts of equations and solve them easily enough. So let's get cracking on this one. Now, the reason why I mention this cot reference in this equation is because as a student, you may go in the wrong direction initially, and then you can end up coming back to the right place at the end, even if you go in the wrong direction. Well, it's algebra. There's no real wrong directions. I suppose there's just the most efficient methods, and then there's methods that aren't quite as efficient. So looking at this equation, we've got a cos x and a sine x, and this is probably where I would want the concept to be fundamental for you. That if you are solving equations with trigonometric identities, and there is a sine x in it and a cos x in it, then there's going to be one of the tricks you're going to have to use. You're going to have to combine sine and x together in some way or shift something, because you can't solve this when you've got a cos x and a sine x. So one way of getting rid of the sine x and the cos x is bringing them together via a division, and that's where we're going to see tan x or cot x. Another way to bring them together could be that last identity, which we're not covering today, cos squared plus sine squared equals 1. And the very last way we might be bringing them together is from earlier content where you do sine 90 minus theta equals cos theta. But you can see in this question, there is no 90 minus x or no pi on 2 minus x. It's all just sine x and cos x. So you need to have a trigger when you just see sine x and cos x in the question that you probably are trying to create a division to substitute in tan x or cot x. So let's go ahead and make a step in this equation, see if we can solve it. Now, if you can't see the path forward, then obviously what you want to do in trig is just start getting things on their own, I suppose. So we're trying to get the trig things on one side of the equation and the non-trig things on the other side of the equation. So you might take a first step here where you do root 3 equals sine x divided by cos x. Okay, that might be a first step that you take. And if it is, it leads you straight into that tan x path and solving. But what I see students do, because they're not sure about seeing the clear way forward, is they might try and divide everything onto the left-hand side. They try and get tan x on the left-hand side because when they see these identities, they've got cot A is on the left-hand side, so they want to get cot on the left-hand side or tan on the left-hand side. Let's just say we did do that in this one. So in this one, now what we're going to do is divide that root 3 off this side. So we're going to have cos x equals 1 over root 3 sine x. And then we have to realize that we've got to divide that sine x across. Students will try and subtract it across. It won't help you. Students at this point might be squaring. We'll talk about that in another lesson. But in this situation, we're just going to divide by sine x. And so we get cos x divided by sine x equals 1 over root 3. And it might seem like to you that we're no closer to solving it. We've still got cos x and sine x, and this is where the trig identity comes in. We were told on the reference sheet that cos x over sine x is cot x. So we make that substitution. Once we've made that substitution, we're in the clear. We're good to solve this. We're probably going to get it at this point. We know that cot x is 1 over tan x. Ooh, I've got some old working down there I need to delete. So therefore, tan x is going to equal the reciprocal of the other side. Ooh, my OneNote screen on OBS has frozen. I'm just going to pause this. Okay, we're back. Not sure what happened there. All right, so tan x equals, so because cot x is the flip of tan x therefore is going to equal root 3 over 1. All right, so now we've got root 3 over 1. Now you may have written that just as root 3, and that sometimes can trick kids or make them struggle a little bit, because the first thing they want to then do is do inverse tan and use their calculator to get solutions. But if we always leave it as root 3 over 1, then it should trigger something in our mind. We remember that we've seen root 3 over 1 many times, and the reason being is that it's in that triangle that we're remembering, though it's on our reference sheet, where we have 2, 1, and root 3. So we can see that the root 3 and the 1 are involved on these sides. Tan is opposite over adjacent, so the angle we care about is down in that corner. And we know that this is an equilateral triangle, so that's a 60, well, it comes from an equilateral triangle. That's 60 degrees in the corner, otherwise written as radians as pi on 3. Now, when we do the inverse tan of this function and we get pi on 3, we need to be super careful, right? For the other part. What does Mr. Hepworth always say? Draw pictures, right? And whenever you're drawing this triangle, you probably should be drawing this thing at the same time. Right? ASTC. Because when we do this inverse tan function of a positive, well, where's tan positive? It's positive here and it's positive here. So we don't just get the one solution. We also get a second solution. Now, going way back up here to our domain, what we're actually dealing with is between negative pi and pi. So we need to understand where that is. So negative pi comes around this way to negative pi, and pi comes around this way to pi. Pi and negative pi are at the same place. So we have one solution in the positive side, which we already found, pi on 3, and one solution in the negative side. So in the negative side, it's in this third quadrant, and the primary angle, I'll just remove that T and the C so we can draw the things. The butterfly primary angles are going to place it down here. Here's theta. So we don't go all the way back to negative pi. We have to move sort of back forwards by pi on 3. So therefore, we go backwards negative pi on 2. So x equals negative pi on 2. That's actually the size of this angle here, negative pi on 2. So therefore, we get our two solutions between negative pi and pi. We got it from tan. We could have got it from cot, but it's nice to sub in the cot and flip it into tan. We could have got it straight from cot, because we also know cot is in this triangle and it's dealing with adjacent over opposite rather than opposite over adjacent. But then we come down into our unit circle and we consider the domain and we get these two solutions. So x equals pi on 3. Oh my goodness, I said negative pi on 2. For those of you that knew that was wrong, calling me out, I hope there's not something that ends up in the comment section before I fix it. Negative 2 pi on 3, right? That's how far the remainder is here. Sorry for my brain fart there. So we've got so we've got pi on 3 and negative 2 pi on 3 are our two solutions for that trig identity where we made a substitution for cot into tan.